Hello students, welcome back. We just completed the end behavior. Now let's go to the local behavior. Here's a motivating example. It's a complicated polynomial, but please note that this polynomial has 3 zeros. From this factor, you get x equals to -4. That's when this thing becomes 0, so 0 times anything is 0. But this one has multiplicity 1. Nothing is there, then 1 power is hidden. Next, x equals to -1/2. That comes from this second factor, and that has multiplicity 2. And finally, this one, x equals to 2 with multiplicity of 3, from smallest to the largest. How about the other factors? They don't do anything because they are quadratic irreducibles. So as far as the zeros are concerned, these really don't do anything there. Now, what if I expand this? Does it help? Not really, just way too complicated. And as for the asymptotic equivalence, well, I can throw all these away. I can get 12 times x to the 12th power. So positive number times x to the even power. So this is going to be a U-shaped graph in terms of the end behavior. As for other behavior, it's hard to tell. Alright, let's graph it and let's see if you have something interesting. Let's see, do we have that U-shaped end behavior? Yes, I can see it, but in case you don't, let's go a bit further. Alright, indeed, this is a U-shaped graph. No problem there. Let's go back to -5 to +5, okay? Now one more thing. Do you see the 0 here? The x-intercept. The graph is cutting through x equals to -4 as predicted from this factor. Do you see that? The graph cuts through the x-axis because that's when the function value, y-coordinate, has to become 0. Okay, how about the other zeros, x equals to -1/2 and x equals to 2? Well, I don't see anything there. So if I don't see anything there, let's zoom in. Okay, let's zoom in. Let's plot only from -1 to +3, and here we go. Now, do you see any local behavior? Yes, I do. At x equal to -1/2, graph increases and hits the x-axis and bounces back, just like a parabola would. And indeed, we have the second power there. Now, how about the next 0 here? The graph increases and then slows down and crosses the x-axis, kind of like horizontally, and increase further. Exactly like a cubic function would. And indeed, we have the third power there. So here's a hypothesis. Does the local behavior around the 0 have something to do with the multiplicity of the 0? The answer is yes. Yes, indeed. And the reason behind it? We have to discuss that, and we're going to answer the question at subsection 3.3. Please be patient. We're going to go back to that local equivalence and the local behavior, but before that, a little bit of a review. Alright, f of x is a real function and f of c is 0, then we're going to say x equals c is a 0 of that function. Everybody remembers that, right? Now, 0 of a function is the same as the x-intercept, as you can see. Y equals to f of c, and that's 0, so y-coordinate is 0. What else? Yes, 0 of a function and the number 0 are completely different concepts. For a function, it can have 1 0, no 0, 2 zeros, many zeros. But of course, in terms of number 0, there's only one. Now, what if f of x is a polynomial function? and it has a 0 at x equal to c. Then you can write something like this. It turns out the polynomial must have the factor of x minus c. So factor it out, and then you may have some other factors. Now, if this other factor also has x minus c in there, and I can factor it further out, dump it all here as much as possible, and here no more x minus c's anymore. If that happens, this m is called the multiplicity of that 0. And as for the other factor here, which I'm going to name as q of x, then it'll turn out that q of c is not 0. Why not? Because if q of c is equal to 0, that means q of x has a factor of x minus c. But then again, if this already has x minus c, factor it out and dump it over to this. But we just assumed we completed doing that. So q of c should be non-zero. Remember this, please. Q of c is non-zero. If you say something like, kind of naively, that's fine. You can understand that, but a little bit more precise treatment will be saying something like this. Using some polynomial expression q of x and adding this, q of c is non-zero. Now, I can do the same thing for each 0. And suppose that we have k zeros, c1, c2, c3, all the way to ck, and each 0 has a multiplicity, m1, m2, m3, and so on. You can summarize all those here. And then no more 0 because, you see, c1 through ck are all the zeros. All the multiplicities all counted in. So what's left, if there's anything, would be quadratically reducible. Kind of like this example. You see, you have some 0 factors or linear factors here, which will give you zeros. And then we have quadratically reducibles, which will not give you any real 0. Okay, so much for the reviews on zeros and multiplicities. Let's go to local equivalence. Kind of similar to asymptotic equivalence in a sense that we are looking for the ratio f of x over g of x close to 1, but instead of focusing around infinity, in other words, x going to humongously positive or humongously negative, we're going to focus around x is close to c. So locally around x equal to c, where c is typically the 0, we want the ratio of these functions to be close to 1. If the ratio is equal to 1, f over g is equal to 1, then f and g are the same. Close to 1, so they're not the same, but they must be similar. And that's what this locally equivalent is all about. In terms of theory, it's difficult to understand because it revolves around calculus. And then, as I told you about earlier, there's subtlety between single dash, meaning the ratio getting close to 1, versus double dash, meaning the difference is close to 0, those kind of things. So things can get really rough, really deep, really quickly. But don't panic. That's not what we are trying to do. Most of the time, we're going to stick to computations, and that's where things stop. So you can factor x minus c out as much as possible. So we have multiplicity m, and then you have q of x, and q of c is non-zero. Yes, we discussed why that's non-zero. Now what you're going to do is plug in x equals to c right here, so that we get q of c, a constant. And then what's left is x minus c to the mth power. So what we end up with is a power function just shifted c units in x direction. That's about it. So everything you know about power function, like U-shape or upside down U-shape, or curved and increasing, curved and decreasing, those kind of things. Everything applies. Now, if you plug in x equal to c to this x, then you get nothing. C minus c is 0, so everything is 0, you get nothing. It's important you plug in x equal to c to other things there. Here's an example. Looks like there are two examples. So we have this blue function, which is a polynomial function, and we are looking at this around x equals to 2. So this factor is the main factor. Everything else here, just plug in x equals to 2, just like here. Do your computation, this will turn out to be 28. So this power function is 28 times x minus 2 to the third power. So positive and cubic power, and shifted 2 units to the right. So around x equal to 2, we have the behavior of the cubic function. Curved, but increasing. Now let's look at in a little larger scale. The blue graph and red graph are completely different because they are different functions. Scale a little bit and zoom in. They're behaving quite close to each other, and now they are almost indistinguishable. That's a visualization of the local equivalence between the two. So this is a way to get a power function which is much simpler than the polynomial function that has the same local behavior as the original polynomial function. Here's another example. Green is the original, and that's really complicated because we have all the x expressions there. But plug in x equals to 2 to all these, and you must leave this because if you plug in x equals to here, we get 2 minus 2, that's 0. Everything is 0, we get nothing. So leave it and plug in x equals to 2 to all these, and this will turn out to be 28. And we have negatives there, so negative 28 times x minus 2 to the second power. So what is this? It's just negative of power function of degree 2, just shifted 2 units to the right. It's a parabola shifted accordingly to the 0 of that function. So the original function must behave the same locally. Here, they don't resemble each other. Here, they kind of resemble around x equals to 2, and now here, you can clearly see they share the same local behavior. So idea is the same, a little bit more complicated, but the idea is the same. What we are trying to get is a little bit simpler function that shares the same local behavior as the original. Original is the polynomial function, really complicated, and a little bit simpler version is actually a shifted power function. The computation of this Q of C part may be a little bit messy because you have to do some messy computation, but it's not that important. Not only calculator can handle it, but it's not really that important to tell the truth. All I care about is whether it's positive or negative, so that this qualitative behavior is, for example, upside down U or just plain U or things like those. So you don't really have to complete all those computations. The key is to get a shifted power function that shares the same local behavior as the original. And how do we get that? By taking this local equivalence. Local equivalence computation can be a little bit more complicated than the asymptotic equivalence computation. And in terms of exam preparation, it's not going to be as important. But in terms of theory, in terms of preparation for what's to come, it takes its own. So please pay appropriate attention here.